Okay, today's run through is going to be a linear Edexcel A-level physics paper for the AS, paper 2 core physics. So it's core physics 2, and this is the 2019 paper. My students are currently using it as a practice run through before their mock exam next week. So I thought I'd try to put this on the system for you. So linear is a new thing added to the channel this year. Usually most of the channel is to do with modular. So the disadvantage with the linear is there's only exams from 2017 really until now. So that's about 2017 to 2024. So 17, 18, 19, 20, 21, 22, 23, 24. Yes, 8 years of exams, whereas if you want to practice more papers, 8 is not that many to get really good at the paper. So I tend to use the modular to prepare students, and then use the linear if that's the exam they're taking, as the practice exam conditions one. Okay, so if you like our videos, make sure you share them with your friends. Make sure more and more people get to know the channel. So it's mainly for A-level. Okay, although there is also GCSE, so if you know anyone who needs help with GCSE, mainly IGCSE Edexcel is the focus. Okay, so to start with, we're going to go through the multiple choice. It says a sample of steel in the form of a wire is subjected to an increasing load. Yeah? Which of the following is the best description of the elastic limit of the steel? Okay? So it's A is about the stress at which the steel undergoes an increase in strain with no increase in stress. Well, I don't even know what that means. The stress at which the steel undergoes an increase in strain. Well, that's not the elastic limit. I think that's just to confuse us. B says the stress beyond which the stress and strain are no longer proportional. Well, that's the proportionality limit. Okay, so when stress and strain are no longer proportional, that's the proportionality limit. Slightly further than that, so just past the straight line portion is the elastic limit. Okay, so C is the correct answer. So C says the stress beyond which the steel becomes permanently deformed. So that's what it means. It will no longer be elastic in its behavior. That means it will no longer return to its original shape or length. And then D says the stress at which the steel breaks. Well, that's the ultimate tensile stress. So that's wrong as well. So the answer is C. Okay, so in core physics 2, which is the year 12 exam, it's mainly materials and waves. But as my students have found out, at the end of the exam, the last 2 questions can be on practical skills, and it can be on any topic. So it could be on electricity, it could be on forces. So you've got to be prepared for that. Okay, so question 2 says radar is used to detect the position of an aircraft. Well, we know that. Microwave pulses are emitted from the radar transducer. Okay, so that's like the transmitter. The pulses reflect from the aircraft and are received back at the same transducer. Okay, so the transducer has a transmitter and a detector or receiver. The time in seconds between the emission and reception of the pulse is T. Okay, so they want short pulses and they bounce off. The distance of the aircraft in meters from the transducer is given by, and you've got to work it out, well, the distance will be the speed times the time. Yeah? But remember, it goes there and back, so you've got to divide the speed times time by 2 because it says and I'm going to change this to green, it says the time in seconds between the emission, so it goes, gets to the car, gets to the plane, bounces back, and reception of the pulse is t. That means the time to go to the plane, imagine the plane's there, then it bounces back. So it's gone 2 distances, okay? So I hope that makes sense. So we're looking for speed times time, and the speed of these waves is 3 times 10 to the 8. So this one's got 3 times 10 to the 8 times t. But you can see here, in this question, they are doubling it, yeah? So if they're doubling it, that's not what we want. We want to have speed times time divided by 2, okay? So it must have 3 times 10 to the 8, and the other two show that these ones are using the speed of sound rather than the speed of microwaves, okay, which are electromagnetic waves. So the answer is C, okay? Question 3 is showing some energy levels in an atom of a gas, yeah? So this is a quantum atom, during which transition, A, B, C, or D, is electromagnetic radiation with the shortest wavelength emitted. Well, when electromagnetic radiation is emitted is when the arrow is downwards, so it's going to be B or D, okay? So it's B or D because the arrow is downwards, and it's when the electron drops that it emits. When an electron drops, it emits a photon, okay? So both of these are emitting photons. A and C are absorbing energy to jump up, so they're getting excitation, and going downwards is de-excitation. Okay, so we want to have the shortest wavelength emitted. Now, the energy of photon, low wavelength, shows shortest wavelength, means that we have a high frequency, which equals a high energy. Yeah, so we're looking for the highest energy change, so therefore the answer is D. Okay? Okay? C is the same amount of energy, but it's absorption. Okay. Question 4 is about the Hooke's law equation, so back to materials, and the equation is F equals K delta X, but they want you to work out the units of K in base units. That means it should be in kilograms, meters, seconds. So F, we know, is the kilograms, meters. F is kilograms, meters, seconds to the minus 2 because it's mass times acceleration, if you can make sense of that. K is what we want to find out, and delta X is in meters. So you can basically put the base units that you know in, and then you can simplify. The m's cancel. So what's missing on the K must be whatever's left on the left-hand side. So K is kilograms, seconds to the minus 2, so the answer is A. Question 5 reads as follows: a ray of light travels through medium 1, so there's medium 1, of refractive index N1, and is incident at an interface with medium 2 of refractive index N2. Okay, the ray is totally internally reflected at the interface. Yeah, so what do we know? We know that the velocity of 1 must be less than the velocity of 2, and we know that the angle I must be greater than the critical angle. So V is less than 1 because it's optically denser. Otherwise it wouldn't be able to totally internally reflect, so we know that the refractive index 1 must be greater than 2. This is just from the information provided. So they give you the speed of light in medium 1 as v1, the speed of light in medium 2 is v2, and they want you to work out which row of the table is correct for this situation. Yeah, well, we already know that v1 is less than v2, so we're looking for v1 is less than v2, so that could be B or D, and we know that n1 is greater than n2, which there's n1 is greater than 2, there's another one, and the others have it the wrong way around. So the only one with 2 correct answers is B. Question 6, which is a core practical, reads as follows. In an experiment to determine the speed of sound in air, a 2-beam oscilloscope, which is there. 2 beams means it's got 2 graphs that you can plot on it. You can have 2 inputs. See, one microphone 1 is going into input 1, and the other microphone is going into the second input. The Y inputs we call it, because up and down the voltage changes. So the 2-beam oscilloscope is used to display the signals from the 2 microphones. So they're picking up the sound, turning them to electricity. The microphones are placed in front of a loudspeaker that is connected to a signal generator. Okay, so this is producing the sound. The microphones, so the loudspeaker is producing the sound and getting to the 2 microphones. It says the speaker emits the sound of frequency F, so immediately we know that the period on the oscilloscope can be measured in terms of 1 over F. The microphones are then placed a different distance from the loudspeaker. The time taken for the sound to travel from the first microphone to the second is T. Okay, so basically, obviously it will get to the first microphone first. Which of the following gives the which of the following expressions gives the phase difference between the 2 signals? Okay, so if you know the period, which we do from the frequency, 1 over frequency, and if we can measure the time, the ratio of the time between them, the phase difference, so you can measure the phase difference of the 2 traces on the microscope, so you can find the time difference between the 2 signals that the microphone produce, because one will be out of phase with the other, and you can determine from that how much in terms of a full cycle it's behind, and therefore 1 over T is F, and if you change 1 over big T to 1 over F, which we have here, you can call it T times T 2 pi F, and one of the answers does in fact come in that form. So the answer is B. Okay, so you just got to be able to play around with these terms. So if you know what phase difference means, you should be able to work it out. So if they were in phase, they could be back like a whole period out, then they would not, you would not be able to tell. Okay. Question 7. The microphones are placed equal distances from the loudspeaker, and the signals are in phase. Okay, obviously because they travel the same distance. One of the microphones is then moved further away from the loudspeaker. Initially, it says the signals are out of phase. Yeah, because if you change the distance, they will be out of phase unless you change them such that they move a whole wavelength or a whole period ahead. After moving the microphone a distance d, the signals are back in phase. That means if you've moved the distance between microphone 1, say that's microphone 1, and then over here there's microphone 2, and the distance between them happens to be equal to a full wavelength, then they'll come back into phase. So the lambda will be equal to d when they come back into the phase for the first time. Okay? They'll go out of phase if it's less than a wavelength, and if you get the distance to be exactly equal to the wavelength, they'll come back into phase. So the speed of sound, you know, is v equals f lambda, and by moving the two microphones apart, you've worked out what the wavelength is. So they want you to work out the speed of sound. V equals f lambda, lambda equals d, so the answer is B. Yeah? Question 8 says, which of the following statements about waves is not correct? So whenever it's a not, they put it in bold. An unpolarized wave may be polarized on reflection from a surface. That is correct. Water surfaces, for example, polarize the light that reflects off it. Longitudinal waves cannot be polarized. That's correct. Only transverse waves can be polarized. And the vibrations in an unpolarized waves are in many directions. Okay? So basically, if you talk about electromagnetic waves, they're actually vibrating at right angles to the direction of the energy transfer in all planes. Okay? It's not one direction that they are vibrating at perpendicular to the energy transfer. They're vibrating at all directions. Okay? It's not a neat thing. And then when you polarize them, then they only vibrate in the plane of polarization. So the answer must be D. Transverse waves are always plane polarized. Now, that's not true. I just told you that they're only polarized when you polarize them. So normally they're unpolarized. So D is incorrect. So the only logical answer is D. So in the AS level exam, there's only 8 multiple choice questions, unlike the modular. The modular has 10 multiple choice questions and then structured questions. So question 9 in the AS paper is the beginning of the structured questions, and you can see in this case it's a 7-mark question and it's on Young's modulus. When you get into year 13, even in the linear, there are 10 multiple choice questions. And in AS, the exams are 1.5 hours, and in year 13, the exams are 1 hour and 45 minutes, and that's the same with the modular exam. Okay, so question 9 says, in an investigation to determine Young's modulus of a material in the form of a wire, which is normal, a tensile force of 14 newtons was applied to the wire. The length of the wire was 2.0 meters, so that's L. The diameter of the wire was 2.5 millimeters, so don't forget that diameter is 2.5 times 10 to the minus 3 meters, and that allows you to work out the area, because that will be pi d squared over 4, yeah? D squared would be 6.25 times 10 to the minus 6. So once you put the answer in, you can automatically get a mark for just working out the area as one of the unknowns that you need to determine whatever it is they're asking us to do. The question continues with information about the length of the wire was increased by 0.2%. So the 0.2% is telling you that the strain is equal to the extension over the length. So X over L, in other words, is 0.2%. Yeah? So 0.2 over 100 is X over the original length, which was 2.0 meters. Now, they want you to calculate Young's modulus, yeah, of the material. Well, Young's modulus is F times L divided by AX, or stress over strain. And I went straight into FL over AX. I always remember that it spells flax. So the force we know, this is the inverse of strain, yeah? So it's 2 over the extension, which I worked out as 2% of 2 meters. So I could have actually just inversed the 2%. So because that is 500, the inverse of 2%, 0.2% I should say. And then the area we calculated before, so you put the area into the equation, and you can get the answer to 3 significant figures is 1.43 times 10 to the 9, yeah, or you can change it to 2 significant figures, because I think most of the data is only given to 2 significant figures. It then wants you to calculate the energy stored in the stretched wire, and the energy stored is the area underneath a force extension graph. So we know F, we know X, so you could just use this equation. Energy stored is half Fx. So we know them both. All you've got to do is put the numbers in, and you get the answer to 2 significant figures as 0.028 joules, and that should go here, strictly speaking. But in this run through, I'm just showing you how to answer the questions. To get the marks in your answers, you need to make sure that your written responses have depth, detail, and clarity. Yeah, you want to make sure that the examiner doesn't have to guess what you're doing. So communicate clearly. It then says for part C, explain why the wire chosen should be as long as possible. Yeah, as long as possible. Well, that gives you a smaller percentage uncertainty. Yeah, and it also makes X more measurable. Yeah, remember that when you put a material under strain, it will get strained. When you put a material under stress, which is force per unit area, it gets a strain, which is a percentage of the length. So obviously the longer it is, the more measurable X will be, and as a consequence, the percentage uncertainty will decrease. Okay, so we'll have a look at the mark scheme at the end, because the way I've done this PDF is the mark scheme's right at the back of the paper. Okay, so that's 7 marks. Question 10. It says a student investigated how a converging lens can be used to project a magnified image onto a whiteboard. Okay. I've confessed, because in the modular, which I normally teach, there are no lens questions, so I haven't done it for a while. So I'm a bit rusty on it, but I think this is a good question to learn about lenses if you are new to it like me, or kind of, I'm new to it in terms of recent years. I haven't done it for many, many years. So I'm just refamiliarized myself with lens theory. In a darkened room, the student placed a smartphone, which is the object in the image formation, 9.0 centimeters from the converging lens. Okay, that means U in the equation is 0.09 meters, and the phone's display was then projected through the lens onto the whiteboard. Okay, the converging lens was 75 centimeters from the whiteboard when a clear image was produced. Okay, so if you put it the right distance, you can get a clear image, and that means V in the equation 1 over F equals 1 over U plus 1 over V, where U is the distance from the object to the lens, and V is the distance of the image to the lens. And the focal length that they want you to calculate is given using this equation. So all you've got to do is to change these values for U to 0.09, V to 0.750, and you put them in the equation with the numbers in, and you'll get the answers. Okay, so F will be 8 times 10 to the minus 2, and I should have put meters. Okay, and that goes there. All right. The next question then goes on. It says the image projected onto the whiteboard was real. Yeah. What is meant by a real image? So it means that the rays pass through the image. Okay. They're not like a virtual image where your eye thinks that's where they're coming from. So the rays actually converge and pass through and meet at the image. So they converge, come together where the image is formed. And of course, the other way you know that it's a real image is that you can actually project it onto a screen, which is what they said we're doing. Okay? So there's the 1 mark. The next part is a bit of trigonometry involved. It says the display on the phone contained 2 dots that were 5.0 millimeters apart. So you've got to change that into meters. So that's 5 times 10 to the minus 3. So we're talking about this is 5 millimeters apart on the phone itself. The student stood 4.5 meters from the whiteboard and viewed the image of the dots. So here are the dots. So on the original, so he's looking at the whiteboard, so this is enlarged, okay, because he's 4.5 meters away. So this is the projected image on the screen. Rays of light from the image of the 2 dots on the whiteboard were incident at the student's eye with an angle theta between them as shown. Okay, so you've got theta, and half of theta enables you to determine the distance on the whiteboard between the 2 dots if you know how to do trigonometry. It said the student could distinguish the 2 dots if the angle theta was greater than 0.0003 radians. Okay, deduce whether the student could distinguish the 2 dots clearly. So we have to work out what theta is. All right, now first of all, remember that there is a magnification involved, and the magnification can be given by the image distance divided by the object distance, which we know from the part done on the previous section of the question. So that's 75 to 9. So the magnification is 8.3 times. Okay, so once you got the magnification, you get 1 mark. All right, then it says the distance between the 2 dots on the whiteboard will be not 5 millimeters, but 8.35 times 5 millimeters, because it's enlarged 8.3 times. So there's the enlargement, and it will enlarge the original distance between dots to a value of 0.042 meters. And therefore, of course, that's 4.5 meters to the screen, but theta doesn't form a right angle with the screen because it's the distance between 2 dots. If we want to have half of theta, then we can use opposite over adjacent. So tan of half of theta will be the distance halfway between the 2 dots, yeah, so 0.042 meters divided by 2, because we want half the angle, and divided by the 4.5 meters, that will be opposite over adjacent. And this ratio gives you that theta over 2, the angle, theta over 2, I should say, theta over 2, it is equal to 0.27 degrees is what I made it. So the theta total will be 0.54 degrees, but we want to put it into radians so we can compare it with the value they're given. And if you do that, 0.54 out of 360, yeah, and then multiply by 2 pi changes the 360 into radians, okay? And you've got to be able to do that. And that gives us an angle in radians of radians. You then compare that to the value given in the question, yeah? And since it's bigger, yeah, it says the student could distinguish the two dots if the angle that he's looking at, theta, was greater than 0.0003, and this is 0.0094, so it is noticeably greater, and you just write, since the angle is greater than the 0.0003 radians stated in the question, it follows that the student can distinguish between the two dots clearly. And that gives you the answer for the 8 marks. Okay? Hope you're finding this useful. I'm going to try to run through as much of it as possible before I break for have a pause for a break. So question 11 we're going to go into. The photograph shows a guitar. The strings of a guitar are at the same tension. Okay? When a string is plucked, a standing wave is set up on the string, along the string, between the two fixed points. There's a fixed point here where the wire is fixed, and then the wire is fixed on the other side here. So you know that the length is roughly from there to there. So the length of the string is also known or can be measured. It then says, and here there's an asterisk, whenever there's an asterisk in A-level questions for Edexcel, whether you're doing modular or linear, it's a 6-mark quality of written communication. So we're looking for depth, detail, and clarity in your reasoning. It says explain how a standing wave is set up on a guitar string like this. So we have the plucked string, so it sends out a wave and then it gets reflected at each end, and the waves travel in both directions along the string between the fixed points that I circled above. And these two waves traveling in opposite directions are said to superpose, which means they just add up, yeah, and they can also subtract, and they, as a result, they interfere with each other, and you'll get constructive interference. I want to do this in green actually. They get constructive interference when they're in phase and antinodes are formed, and when they are out of phase or in antiphase, exactly half a cycle out of phase, they get destructive interference and you get nodes. And the nodes can't read my own writing, minimum or zero displacement or amplitude. Okay, so the nodes form, for example, you'll have nodes at the fixed points. You'll have nodes here and you'll have nodes there. Okay, so you have nodes at the two ends, and you can create nodes in the middle as well, depending on whether you're looking at the first harmonic or the second harmonic, etc. So then it says antinodes are places of maximum displacement. That means where you have set up constructive interference, or when constructive interference occurs. And as I've mentioned before, nodes also occur at both ends, which are the fixed points. So that's how standing waves are set up. I have 2, 4, 6, and 7 points I've made. So if I wrote these out in a clear, lucid fashion to explain how standing waves are set up, hopefully most of these points, a lot of these points will be on the mark scheme. Okay? So you get 4 marks out of the 6 just for mentioning the correct terminology and the content, and then they'll give you 2 marks for the clarity and the reasoning and how you linked your points together. A bit like I just did by speaking. Okay? So part B then says, in the same theory, a thicker string produces a note with a lower fundamental frequency than a thinner string, yeah, if they're made of the same material, okay? Because a thicker string basically has more mass per unit length, and that's the mass per unit length is the thing that you need to use in your equation. And the equation for a speed of a wave on a string is v, speed, is equal to the square root of tension divided by the square root of the mass per unit length. So this is relating to that. So you can see the thicker string will have a bigger value of mu, yeah, so the velocity will be less. And you also know that velocity equals f lambda, so you can change v for f lambda and you can come up with this equation, which is commonly used in AS level, okay? So you got to justify why the frequency is lower for the thicker string, okay? So thicker means that mu is greater, yeah? So we're talking about mu being the mass per unit length. Thinner means mu is less, and the length we said is constant. As we said, the tension before was constant, so tension and length, so tension also was constant. I haven't put that in there. And because the length is constant, we know that the wavelength will be linked to the length, so that's related. So the fundamental frequency will actually occur when the fixed points, the nodes at each end, yeah, so the length is from there to there, and from there to there. Now you can see that's half a wavelength, yeah? So here you know for the fundamental frequency, L equals to lambda over 2. So you can replace lambda in this equation with 2L. Okay, and that's a common trick in these questions. So once you've done the mathematics, explain that this is the wave equation, and use algebra to replace v with f lambda, and you want f to become the subject of the equation, then f equals 1 over lambda, yeah, and you have to say that the lambda is linked to the length and the lengths are the same. So the only variable is mu, and if mu is thicker, then frequency will be lower, yeah? So if mu goes up in this equation, it is the reason why frequency, so it's meant to say frequency will go down, okay? Frequency will go down if mu goes up. And that's justifying the statement, okay? So if you get all those points into your clearly written answer, you will get another 11 marks, okay? All right, so next question is question 12. It says, the photographs show an image of 2 pancake volcanoes. They look like pancakes, so that's what they call them, on the surface of the planet Venus. Scientists believe these types of volcanoes are formed from lava spreading out in all directions onto a flat landscape. Okay, so if lava has a viscosity and it will flow until it evens itself out. A student investigated the formation of pancake volcanoes. Yes, they didn't go to Venus, mind. She observed the flow of a viscous liquid at 2 different temperatures as it spread out from a central spot. Okay, so that's the model that they're using to investigate how pancake volcanoes can be formed. Now it says the photographs below show the liquid at both temperatures after it had been flowing for the same length of time, so it's a controlled variable. same length of time. So you can see the high temperature test has spread out more from the center than the low temperature. Yeah? They changed the independent variables temperature, and how much it spreads out is what's measured, and they've controlled the amount of time that they've done it for. Obviously, that makes it a valid experiment. Okay, scientifically valid. Okay, it says scientists believe that at the high temperature of the lava, when it erupts, is one factor that allows the lava to spread over a large area. Okay, makes sense? Explain how the student's investigation supports this idea. So now again, you've got to put your thoughts into a clear rationale. So it says high temperature, these are my bullet points I want to include. High temperature tests show that the liquid spreads further in the same time. Don't forget to say in the same time, because remember, that was a controlled variable. It shows you're taking account of the detail. If lava behaves, I've said, in a similar way, it would support this idea that higher temperature equals lower viscosity. Now, my year 7s know that because we did an investigation of heating oil and seeing how it became more runny, okay, which is less viscous. So I think those 2 bullet points should hopefully get me the 2 marks, and we'll have a look, or you can have a look at the mark scheme later on. Now, part B says the student carried out an experiment to determine the viscosity of the liquid at room temperature. She observed a steel sphere falling through the liquid. Now, that's another core practical from the materials topic. Yeah, viscosity. So you need to be familiar with the details. She had the following equipment: a long, wide cylindrical tube, 2 steel spheres, diameters slightly different, well, 3 times bigger actually, roughly, a video camera to record it, the motion, a meter ruler, okay? The student observed the sphere with the diameter of 7.0 millimeters falling through the liquid. The sphere fell 0.80 meters in 5.3 seconds at constant velocity. So we're talking about terminal speed, yeah, being reached, okay. All right, the viscosity eta, that's the Greek letter, can be calculated using this equation. So they've given you an equation, and they've given you the details of some of the constants, and they say this is a valid equation providing Stokes' law applies. That means they expect you to know what Stokes' law is, which is F equals 6 pi eta R V, where eta is the viscosity, R is the radius of the sphere, and V is the speed that it travels at. But they've given you an equation that they want you to use. Now you know that we are given, this is now the solution, gravity we know, G, so there we know G. We know that volume is 4/3 pi r cubed for a sphere, so you've got to use volume to put it in there. We know the diameter is 7 millimeters, so you've got to change that into meters, and then you have to, you can then work out the radius, yeah. Then you can work out the volume once you know the radius. So I've done that over here. And of course you can work out the velocity from the distance and time. So that's another one you can do quite quickly. And it looks like you get a mark for this. You get a mark for working out the volume 4/3 pi r cubed. Yeah, and that gives you an answer of 1.8 times 10 to the minus 7 meters cubes. So it looks like we've got 2 marks already. Yeah, how many marks is this section? Have I missed it? Where does it say that? Oh yes, here it is. 4 marks, I think it says. Okay, so then eta, the rest of it, you want to put whatever you can into the equations. So we know volume, put the volume in, yeah. So that's been put in. There it is, the first figure. G, the 2 densities, yeah, which are given here, these 2 densities, have to go into the equation as well. So once you do that, 6 pi underneath, that's the top done, 6 pi at the bottom, RV, okay, R is here, that's R, so I've put that here, and V there. So that gives you an answer of 1.13 Pascal seconds to 3 significant figures. Hope that makes sense, even with all my yellow and green scribblings. And you can then round it up, I've suggested, to 2 significant figures. But I think 3 is fine as well. So 2 or 3, I think, should get you the marks. And here we're going to probably stop after this because I think I'm tired of talking. Part 2, it says, if the student had used the larger sphere, the question would not have produced the correct answer. Yeah? Can you explain why? Okay. Well, this is what I put. With the larger sphere, the terminal speed required would be larger. Yeah? Why? Because the weight would be greater. It's heavier. So to balance the weight, you'd need to go to a higher speed for the terminal speed to create the viscous drag equal to the weight. Yeah, remember that you're going to have the weight downwards and the viscous drag upwards. And when these two are equal, then you'll have terminal velocity. So the flow would be would no longer be laminar at such high velocities. Yeah, and turbulent flow means that Stokes' law no longer applies. And the question on the last page, they say that equation is only valid if Stokes' law applies. And Stokes' law requires spherical objects, relatively low speeds to preclude turbulence. We don't want turbulent flow. It only works with laminar flow. Finally, the students use the video camera to record the sphere falling through the liquid. State one benefit of using the video camera. Well, that would eliminate human error for timing. And you probably have alternative answers in the mark scheme, but it's only 1 marker. So that's what I've put down for my attempt of the 1 marker to get the 9 marks. Okay, I'm going to go straight to the mark scheme at the end of the paper, and then hopefully come back and do the rest of it later on. So here are the multiple choice questions. They don't give you as much explanation as the international A-level questions. So I think the mark schemes and the explanations in the IAL, the International A-Level, are slightly superior to the linear. But both of them are better than AQA, which I've also taught. So I would recommend, while you're practicing and learning the course, go and use as many of the IAL papers, which you can also find my solutions on this website, on my channel, and use that to improve your understanding of the concepts. And then when you're ready, go and use the linear for your practice exams under timed conditions. And there's question 8 at the bottom, so you can stop the video and have a look at your own answers, and you can go and correct mine for me. Question 9, I've added the few notes. It was about Young's modulus, it looks like. So I've done some calculations which they hadn't done perhaps, or I wanted to do for myself. So they've got 1.4 here for E. I've put it to 1.43. I haven't put the units, newtons, meters to the -2. Question 10, the one on the lenses. Question 11 was the 6 marker. What was it about? Oh yes, how do you set up a standing wave? So here are the 6 things they're looking for. 6 of them, okay? And of course the examiner will look at the quality of your written answer as well, so it's not as simple, but it does give you an idea of how well you've done. Question 11b was the mathematics of the calculations, which we talked about. So there's 2 ways of doing the last 2 marks. You either do it this way or this way. I can't remember. I think I probably mentioned both. 12. So this is about the viscosity. And they'd made a mistake here, so I corrected it. They had eta in the wrong place, so hopefully you can read my correction. Yeah, and those are the last 3 points that they're accepting. So I'll let you stop that, and that's the 9 marks. Okay, so we haven't gone through the next bit, although I went through this with my students the other day in class. Okay, so that's the end of this first video. Sorry it's a bit long, but I wanted to get it done before tomorrow to help my own students, and I don't know when I'm going to do the next part. Thanks for watching. Don't forget to show your appreciation, like each video you watch, don't just watch them. Share them with anyone else you think will benefit, and subscribe so you know when future videos are uploaded. And once again, don't forget to use the international A-level papers to help improve your understanding. And Swarali, if you're listening, or if you ever do, remember, the more papers you do, the better you get. Thanks for watching. Bye for now.